All right, here we are. This is atomic structure and periodicity unit. There's multiple sections. First section is atomic theory, and then the next section is periodicity, and then there is nuclear, but we're going to kind of gloss over that because nuclear, they don't really focus on that in IB. That's more of an AP chemistry. And then the last section is going to be complex ions, which they don't really focus on AP, but they do in IB. So you get different flavors for the different kind of program. With this, instead of having one big test, you can't really have one big test on this in 40 minutes. So there's going to be 3 little tests. One for atomic theory, one for periodicity, and for complex ions. So that's how that's going to happen. And I got to check the schedule to see when the first one is. The first test, close. It's like next week, I think. I got to double check, but I think it is. Yeah, so it doesn't matter because it's term 1, term 2 is going to be like semester 1 grade. It's all 1 grade. It doesn't matter.
Oh, yeah.
So because it's a year-long skinny.
Wait, next week is finals.
Next week's finals, yeah. How is that going to work? So next Thursday, let's pause this. All right, let's get rolling with this. Atomic theory. So it's not a whole lot. It's stuff that you've done in your sophomore year chemistry. So we're going to be kind of reviewing and then kind of taking it to the next level. So it shouldn't be too bad. Redox is a little bit more difficult because it's the first time you've seen it, and it's not. It's tricky. Reading assignment 2.1 is on Canvas. So I'll be working on that this week. And yeah, it's looking at a little bit of nuclear and electron placement, electron configuration. So atomic theory, we're focused on what makes up an atom. You got protons, you got neutrons, you've got electrons. Here's a bunch of information. You're not required to memorize it. A lot of it you already have memorized, like protons are positive, electrons are negative, neutrons, no charge. AMU stands for, any ideas? Atomic mass unit is based off of the carbon atom experimentally, and that's our standard of comparison. And they created a new system because I didn't even write the number down here, but it's a super number, and it's inconvenient to have to write that all the time. So they created a new system, said, oh, 1 AMU approximately is the mass of a proton. Same with the neutron. Electron is basically 0 AMU, but it does have mass. It's a small amount. All right. Moving on. Yeah, AMU means atomic mass unit based off of carbon-12 atom. We got ions and isotopes. Without looking, oh, I can't. Do I cover it? You still haven't found you. What's the difference between an ion and an isotope? Any ideas? Without looking.
Isotope is a different number of neutrons.
You got it. So isotope has same number of protons but different number of neutrons. That's the difference. Whereas a ion has same number of protons but different number of electrons. So ions and isotopes. Which subatomic particle, proton, neutron, electron, determines what the element is? Proton. You got an atomic number. If it's not number 1, then it's not hydrogen. All right. So then we got electromagnetic spectrum. This is basically the frequency of light. You got radio waves to microwaves to infrared. That's like the night vision goggles. You've got visible, which is just a little blip in the entire spectrum. So basically what we see and perceive is just a small fraction of the entire universe. Ultraviolet, UV rays, X-rays, gamma rays, all of that stuff's bad for you. It's going to penetrate further because it's higher energy through your skin and into your DNA and kind of mess up the sequence of DNA causing cancer. So,
that's why they put that pin around you.
yeah, basically lead so it doesn't go
Oh,
through.
I thought it was for, like, it doesn't mix up the picture. I didn't think it was for my safety. No, it was for yours.
It's for your safety.
Oh,
Yeah.
I thought it was like, so like the rest of your body doesn't mess up the picture.
My wife's grandfather worked in the lab all his life, and he ended up dying of bone cancer eventually. So, and I'm sure he did the safety protocol. So yeah, you want to be careful around X-rays. We don't really have to worry about gamma rays, X-rays, or UV too much because we have this molecule called in the atmosphere ozone. So the ozone layer is O3, and what it does is it creates a protective layer that causes these rays not to penetrate. They just can't go through. And fun Earth science fact is land first appeared, not land, animals first appeared on land. When was it? It was around 300 million years ago during the Silurian period. And what happened in the Silurian period was the ozone layer first appeared. So once the ozone layer appeared, life can be on land. Fun Earth science fact. Here's a bunch of words, but let's summarize it. We need to focus what's low energy, what's high energy. So over here we have low energy. That would be the radio waves are the lowest energy, and the gamma rays are the highest. What causes cancer? Low or high energy? High energy waves, you got it. The low energy waves are pretty safe. And if we're drawing a wave, there's a nice little radio wave. And there's a nice little gamma ray. And what do we notice about wavelength?
The higher it is, the more frequency.
The higher the energy, the higher the frequency, and the shorter the wavelength. You got it. So higher energy, high frequency.
Does the wavelength get bigger?
The wavelength gets shorter. And these would be good multiple choice questions that IB would ask. So the shorter the wavelength, the higher the energy, higher the frequency. The lower the energy, the lower the frequency. And longer. I'm going to do the Greek symbol lambda, which stands for wavelength. All right, it says wavelength is a distance from the point on one wave to the same point on the next wave. So that would be crest to crest or trough to trough. That's a wavelength right there. And typically it's in meters. In meters. All right, frequency is defined as the number of wavelengths that pass at a given point in a second. It's measured in hertz, also known as 1 over seconds. So that's going to be important when we're doing some calculations. Because this is the part, we did this in sophomore level chemistry, but we didn't do the math part. So this is going to be the math part that we get into. So light technically refers to all the wavelengths on the electromagnetic spectrum. Since light travels at the same speed, there we go. This is actually given to you in your data booklet on the first page, table of constants. Speed of light is 3 times 10 to the 8 meters per second. If you took physics, you probably have it memorized. Anybody take physics? Oh, so you guys got it memorized, right? No. Okay. Good thing you don't have to memorize it. It's on the data table. Different types of light simply depend on the wavelength, frequency of that light. All right, so that brings us to the gray bow, also known as the rainbow if it was in color. This is Roy G. Biv. So I'm going to help you out and label these shades of gray. This dark gray represents red. The lighter gray is orange. Okay, you can see it?
No, we can't.
Oh, you can't see it. Oh, let me see it. Okay. Blue. Some people don't agree with indigo. Depending on the scientists, I think they got rid of the color. But we'll put it there so that we can say Roy G. Biv. Indigo. Indigo would be kind of like a purpley blue. which is my worst nightmare because I'm partially colorblind and purples and blues. All right, then we got 700 nanometers to 400 nanometers. Red is closest to radio waves, and violet is closest to gamma rays. So which color has the highest energy? Violet. Violet has the highest energy, so it's 400 nanometers is the length of one wavelength for violet. And red is going to be 700 nanometers. So remember, the longer the wavelength, the lower the energy. The shorter the wavelength, the higher the energy. And we're going to be getting into this doing the Rydberg constant lab and looking at the line spectrum that hydrogen produces. But based off the electron arrangements of each element, they're going to absorb different amounts of energy. And we can see that by putting a current into that gas or element, and it exhibits a line spectrum. That's a unique fingerprint. We're going to get into that a little bit. But before we do that, let's get going with some of the math.
Oh, yeah.
That's lambda, which is wavelength.
Yeah, but is it just like an upside down Y, or is it not?
It's a Greek symbol, lambda, so it's not a part of the
Alphabet.
alphabet. What do you call our alphabet system? Okay.
ABCs.
There's a fancy name, like there's the Greek system, the Arabic system, and I forget what this one's called. Maybe the Latin one? I don't know. All right, so with we're going to be getting into quantum mechanics, which is looking at the arrangement of electrons in an element and quantifying the energy absorbed and released by those electrons. In order to understand this, you need to know that there's two different models representing something that we can't see, which is an electron. One is the wave model, the other is the particle model. We're pretty much like blind people from India feeling an elephant, not knowing what an elephant is. So, yeah, it's like a fable or a story. So one person touches the trunk, they think it's a snake, and they think it's a tree. Well, so you're looking at it from different angles, basically. So here we got the wave model, which is looking at electron through the perspective of it being like a light wave, which is true, but then there's things that don't fit into it as well. So we have the particle model that fits the other side, which takes into the account that an electron actually does have mass. Even though we said it's basically 0 AMU, it still is a percentage of an AMU. So we have to have two models to kind of describe this, and that's what quantum mechanics is looking at. We got C equals F times lambda. C is the speed of light, F is frequency, and lambda is the wavelength. So we might want to write those down. So this is saying that the wave model says that it acts like a wave, electrons, because they're so small. It acts like light. So C, speed of light, which is, anybody remember? 3 times 10 to the 8th meters per second, and that's in the data booklet. F is frequency, which I believe is in hertz, also known as 1 over second. And then lambda looks like an upside down Y, Greek symbol, wave length. All right, so, and it can also be act as a particle. Well, it is a particle, but it acts like a wavelength also. Energy of electron. That's energy. And energy is typically in what unit? Joules, or kilojoules. In this case, it'll be joules. H is Planck's constant, named after Henry Planck. And this is also in the first data table of constants in your data booklet. 6.626 times 10 to the negative 34 joules times second. So this is a unique constant that works out in all of these equations. And then F we know is frequency. Hey, and then we got an example problem there. Perfect segue. All right, it says how many joules of energy does a single photon of red light contain with a wavelength of 762 nanometers? All right, what do you think the first thing is you need to do? Yeah. I didn't hear what you said. I'm just saying yeah.
You gotta like decide which equation to use.
Yeah, exactly. So we've got wavelength. Which one of these equations has wavelength in it? The first one, yeah. So you're going to use that one. Hey, our speed of light's in meters per second. Is that going to be problematic?
Sure.
Yeah, unless we convert something. I would convert the nanometers to meters, and then you can plug it into the equation. All right, so 762. Oh, all that factor label from algebra way back when. So we got meters, we got nanometers. I always give the bigger unit a 1, and then my exponent is going to be positive for the smaller one. Oh, man. Do you guys remember King Henry?
Yep. Yes.
King Henry
Yeah,
died
you
by
drank chocolate
drinking
milk or
chocolate.
something?
Yeah, and then he made Nancy pout.
No, I didn't hear that part.
So I always go for this just so I don't have to deal with it this year. So yeah, we got base unit is meter. We're going 1, 2, 3. 1, 2, 3. But then milli to micro is 3 steps. Micro to nano is 3 steps. So it's a total of 9. So we just put 10 to the 9th on the bottom, and there you got it. If you're going the other side, it's tera, giga, mega, like computer science. It's the same deal. It's over 3 spots. Oh man, I'm going to need a calculator. Oh, a lot of zeros.
Oh my god.
1, 2, 3, 4, 5, 6, 7. All right, there it is. So I'm just putting in sign of notation because I don't know how many zeros those were. But we got 7.62 times 10 to the negative 7 meters. That's our wavelength. Our frequency, we don't know what the frequency is. But we do know speed of light is 3 times 10 to the 8th meters per second. Then some more math. 3 times 10 to the 8th divided by 7.62 e. Make 7. All right. And when you get more experience to the power of 14, if you got that as an answer, you're probably right. So frequencies, when you're dealing with energies of electrons, is around that ballpark. All right, so frequency equals 3.93. I'm not going to worry about sig figs till the end. And that's hertz, or we're going to say, if we divide both sides by meters, our unit is left with 1 over second, which is hertz. I'm going to put it 1 over second. All right, so that gives us frequency. Ultimately, what's the question? How many joules of energy does a single photon of red light? Now you use the second equation. You got it. Yep.
Yes.
Energy of electron equals Planck's constant 6.626. Where is it? Times 10 to the negative 34th. Oh, there it is.
That's your answer, right?
And that would be your answer.
Hi, sorry.
It,
I understand now.
okay. And then if you notice 1 over second, like if we just put hertz, it's like, well, how does that cancel out? Well, because hertz is 1 over second, and seconds cancels out, and you're left with joules as your unit, times 6.626 e negative 34. Yep, and to the negative 19th, that's going to be kind of your ballpark range for energy of an electron. So that's 2. We're going to go with sig fig rounding. There's 1, 2, 3 in our original number, 762. So we're going to go with 3 sig figs, which is 2.61. Times 10 to the negative 19 joules would be the amount of energy that are within a red light, 1 photon. So not much energy at all, because it's super, super small. And then if you notice, Einstein's equation, E equals mc squared, speed of light squared times mass equals energy. Mass is energy and energy is mass. It's all kind of interchangeable. But it cannot be created nor destroyed.
Why did you put 6.62? That's the constant. That's the constant.
Yep. Planck's constant times frequency equals the energy of an electron. So there's 2 equations you got to do. We're doing both models, the wave model, the particle model, so that we have a full elephant. So. All right. So Balmer series, we're going to be dealing with this in the lab. I think Thursday we got slated for the Rydberg constant lab, and then we got another lab. It's lab. The equipment doesn't really work, so I'm going to cheat and give you like what you should see through the equipment. It's like thousands of dollars too. It's kind of a bummer. But. All right, so Balmer series. What we got right here. Here's the Bohr model. The Bohr model is really only good for when we're talking about energy, which is exactly what we're doing right here. So that's why we have the Bohr model. Are electrons really moving around in orbital circles like that? Absolutely not. We can't even pinpoint. We only can pinpoint the approximate zone of probability of where they can be found at any given time. But for the sake of energy, this is a nice model. And so we call it N. We could say, oh, does it say it right there? Yeah, well, N equals 1, 2, 3, 4, 5, and so on. Those are the different energy levels. And if the electron, let's say it's going from energy level 6 to energy level 2. So we're going all the way from 6 all the way to 2. And when it does that, it releases energy in the form of violet light in that certain situation. So the electron is in the high energy state or excited state, and when it goes down to its ground state, it loses energy in the form of light. So it takes more energy for an electron to be far from the nucleus. Closer to the nucleus, the less energy. So when it goes down to its ground state, it releases energy in the form of light, and it's violet. If it starts at the 5th energy level and goes down to the 2nd energy level, it loses energy in the form of blue light. And if it's from the 4th to the 2nd, green, blue. And if it's from the 3rd to the 2nd, orange, red. So what's unique about the Balmer series? Any ideas? Can you end at the 3rd energy level or the 1st energy level?
No.
You could, but then you wouldn't be in the Balmer series. So what's unique about the Balmer series is they all end at the 2nd, at 2, energy level 2. And why do we talk about the Balmer series the most? Because it all fits in the visible light spectrum, which is super convenient. Because then if you go to the Lyman series, all these have electrons returning to the ground state at n equals 1. So there'd be a higher energy difference. What do you think it would be? Infrared or ultraviolet? Ultraviolet, because it's higher energy. And there it is. So, and then you got the Paschen series, which is ending at energy level 3, which would be less of an energy difference. So those would all appear in the infrared. And if we had sophisticated equipment, we could focus on those, but we don't. Even this equipment, looking at the visible spectrum, is expensive. And it doesn't always work. Here it is for hydrogen. hydrogen has 4 lines, and there you go, 1, 2, 3, 4. Those are the 4 different lines that appear. Do other elements potentially have more lines? Yes. It all depends upon the number of electrons that are present. We're just going to be focusing on hydrogen. Fun fact, how do astronomers know that stars are made out of hydrogen and helium? This. Yeah, they look at the stars through a telescope that has certain prisms that produce a line spectrum, and they can determine the percentage of hydrogen versus helium that a star contains. That's how they study stars and know that older stars have more helium in them. Can they look for water on other worlds outside of our solar system?
Yep.
Yes. So in order to have water, we would assume that most likely there's a high level of oxygen present. And it's really the oxygen element isotope spectrum they're looking for. And have they found that yet anywhere?
Yep.
Have they?
I don't know.
No, that's news to me if they did. Oh,
I did.
I know as of last year, I don't think they did. Maybe they did this year. I don't know. But that would be revolutionary because that would skyrocket the probability of there being life outside of our planet.
Yep.
What was it?
What did you say that they're looking for?
They're looking for the signature of oxygen from other worlds. I don't think they found that yet.
Yeah.
I'm gonna look that up after this class.
When they talked about when they thought there was once water on Mars because of like
Yeah, there is water on Mars. There's ice on Mars right now,
ice.
and they do believe that there might be subglacial lakes with liquid water.
Okay.
But some probes are giving information that there isn't, and some probes are saying that there has to be liquid water. So they're not totally sure, but
Weird. Okay.
yeah. So they'd have to send a rover down there and dig down in the ice. But yeah, there's definitely probably water on other planets because it's a very prevalent molecule in the universe besides hydrogen. There's water on Mars. So now it's just a matter of if you find oxygen, well then there's probably water and probably life. Because oxygen on Earth came from cyanobacteria, which is life. So otherwise it would be like Venus or Mars. So application of why you need to know this stuff, you're not going to go into chemistry. Well, if you want to do astronomy and other things, you could know about it. All right, what are we doing here? General principles of quantum mechanical model. So this is just describing the quantum mechanical model, and that's talking about the S, the P, the D, the F, the little sub levels of those. Ring a bell? Way back when. All right. We're going to go over it. Unlike Bohr's model of the atom, we're unable to isolate the location of an electron around the nucleus of an atom. So that's called the uncertainty principle. We never know. Is it here? Do I have it? The uncertainty principle. No, I don't have it. Yeah, I guess it's talking about the uncertainty principle. Basically, let's write that down. Uncertainty principle. It's the Heisenberg uncertainty principle. Cannot pinpoint exact location of electron at any given time. So, like before the age of cell phones, Facebook, and GPS tracking, when your parents sent you to school, they would know that around period 5 you're in room 338. But they don't know what seat you're in. Although nowadays your parents might know what seat you're in. So I know Google knows where I am all the time. They send me an email once a month saying exactly where I've been. It's like, I know. I don't know.
Must be like subscribed or something.
You're on a watch list.
Yeah. But even if you're not subscribed, all that information is recorded. And
Yeah, you can request a release too. I've done that.
Really?
What they have on you.
All right. So, guys, the quantum mechanical model, it works, but even that's not foolproof. Only 90% of the time. So when we got those spheres of probability, like the circle shape or the little bow tie shapes or the flower petal shapes, we'll get to that tomorrow, talking about what these three-dimensional shapes look like and where these electrons can be found. They're only going to be found there 90% of the time. Sometimes they might be outliers, potentially. But I think that's all we got time for, so we're going to pick up on this tomorrow. Homework is on Canvas, the reading assignment. We got Pearson, we got Zoomdall. Start reading and answering the questions. You only have like a week and a half until the next test. Yeah, that's the downside about having like 3 tests in 1 unit. That's that. All right.